All right, hello everybody. Today we're going to be talking about the simplest form of stress, which is axial stress. And what we're really talking about is an object under either tension or compression. So if I had some kind of little cylinder here and I were to put some kind of force on here, in this case we're going to say 50 kip force, clearly in tension, and we'll have some kind of cross-sectional area of this cylinder that is equal to 2 inches squared, and we are interested in what kind of stress, or what stress even is, on this cylinder. So let's start by defining what stress actually is. And really what we're talking about is the average normal stress. And the reason we're saying average is that we're basically saying if I were to have a cut somewhere in here and look at what's going on internally, what we're really saying is across that whole cross section is where our stress is occurring. We're pulling up with this 50 kips, and across this little cross section you could almost envision distributed evenly throughout this entire cross section, or the average stress across that cross section. So of course it can be either compression or tension. I have it drawn in tension. I should point out that with this term normal, what does normal mean? Normal means perpendicular, or another way that you'll hear it often called, in fact I'll do this quite a bit, is I'll call it an axial stress. Axial stress meaning it's this long axis of our material. Our equation for stress is basically just a force over area, and the symbol we're going to designate for stress is a sigma. So we have some kind of force divided by area. Our first real equation in strengths. Pretty exciting. Hope you're excited. I know I'm excited. And what this really says is that our average normal stress is equal to our load divided by our area. And we have to take a minute here and talk a little bit about units, because units become really complicated for some reason for students in strength and materials. If we look at our general units of load over area, and looking at our standard units, or US imperial units, what we see is our standard units would be a pound force over square inches. However, we aren't actually going to use that very often, if ever, unless it's a very small load, because most loads get very large. Instead, I'm just going to say you should use kips. And a kip, as a reminder, is just 1,000 pounds over inches squared, and we're going to designate this as KSI, kips per square inch. In the metric system, our basic units would be newtons over meters squared, and you might remember that Newton over a meter squared is equal to a Pascal. However, once again, we're going to somewhat vary from this. You can use those standard units, but I think you'll be better off if you were to use newtons and millimeters. Reason being is most of our measurements, when we're designing things, meters are just too big. You end up with so much scientific notation within your equations, it becomes confusing. So stick with millimeters, and a newton over a millimeter squared, you could probably do the math yourself, but we end up with a megapascal. So here's what I recommend in this class anyways. I recommend that whenever you have a force, a lot of times they'll be in kilonewtons, put all of your forces into newtons, put all of your lengths into millimeters right when you start the problem, and then when you're calculating it, you can follow all your units. However, you can pretty much be guaranteed that what you're going to end up with anytime you have a stress is megapascals. So when you're working forward and backward, you're working with megapascals and millimeters and newtons. So looking at our stress up on our little example, when I have the 50 kip force in an area of 2 square inches, we can see that our stress, so this is from the example, we can see that our stress would be equal to P over A, or 50 kips over 2 square inches, which is just 25 KSI. Now the question you should be asking then is, would this be an acceptable stress for whatever we're designing for? And that's why I said this class is such a great class, because this is the first time where we're actually designing things. And so at this point, anytime, say we're looking at steel or something like that, we can just go into a table and actually look this up. So in the back of the Hibbler book or posted on Blackboard, what I have is a table of different materials. And in this case, there's 2 of them. There's one for standard units and then one for metric. And so if I were to say that I'm going to make this out of steel, let's say I'm going to make it out of an A36 steel, probably the most common steel. I have these different values up top, and what I would typically be looking at is what is the yield strength, and we'll talk more about what the difference between yield and ultimate is later. But yield is right where the material starts to permanently deform, and we are under tension. So what I see is that I could have a sigma y of 36, and that's where it starts to yield. Well, so as long as I'm under 36 KSI, then I know that I have not permanently deformed my material, and it would be an acceptable material. Of course, you could go through and work backwards and say, well, what if I wanted to make it out of magnesium alloy? And I see, oh, it can only handle 22, so that would not actually work. So, but the idea is that with this axial stress or average normal stress, you can use your table of materials to figure out either the material strength or work backwards. You know, what kind of area would be needed to support this 50 kip load. You would just plug in your stress, leave it in KSI, leave your force in kips, and then you'd end up with a area in inches squared. So let's take a look at one more quick example, call it a day. Let's say I had kind of a truss system, and this truss is going to support a load of 1,000 pounds, or 1 kip. Dimensions, we're going to have a 4-foot cantilevered height out, and also a 4-foot distance between these 2 members. So we can talk about these things. We'll call this point A, B, and C, and we're going to have different sections in here, or cross sections. BC is going to be like a hollow pipe with a 3/4 inch outside diameter and a 1/2 inch inside diameter. And we'll say that AB has a rectangular cross section that is 1 inch tall by 1/2 inch wide. And what we would like to do is find the axial or average normal stress in both of these members. So the first step in this problem is that I need to find the force in each one of the members. So I'm going to go to my statics and draw a free body diagram. So if you can't quite remember how to do method of joints on a truss, you might want to review that material, but that's in essence what I'm doing. I'm looking at joint B. I do know that this is a 45-degree angle, and so from my statics I could say sum of the forces in the y direction equals 0, and that gives me this FBC, but I need the vertical component. Sine 45 minus the 1,000 pounds is equal to 0. So my force in member BC is 14 pounds, and that is in tension. And I remember, hopefully you do remember, that if the arrow is pointing away from the joint, then the member's in tension. If it's pointing towards the joint, it's in compression. Same idea in the x direction. We'll statics review, and that gives me an F in member AB that's equal to 1,000 pounds. In this case, it would be in compression. Now, I will say that often what we'll do in strengths from this point forward, maybe you should get in the habit now, is if it is in compression, we're going to put a negative sign designating compression, and tension will be positive. But or we'll just keep it straight right now by calling them in tension and compression, either way. When we come to the stress then, we know stress is equal to P over A. So for AB, we'd have the force in AB over the area of AB. So the force being 1,000 pounds. Actually, I told you let's use kip, so let's go ahead and do it. So we're going to have 1 kip force over cross-sectional area. And if I look up at AB, it's a 1 by 1/2 inch. So we have 1 inch by 1/2 inch. And that gives me like 2 KSI in compression. Or if you would have watched your sign, you would have had a negative 2 KSI either way. Probably wouldn't do both. I wouldn't say -2 in compression. It's almost like a double negative type of thing, right? For BC, we have same idea. So I have 1.414 kips over cross-sectional area, pi over 4. The outside diameter is 0.75 and the inside is 0.5. So just finding the area under the stress, and I end up with 5.76 KSI, and of course this one is in tension. So that wraps up this video. Hope it was enlightening, and I'll look forward to talking to you all next time. Have a good day. Thanks.